So the other day, I spent, I don't know, a solid 20 minutes frantically tearing my house apart, looking for my glasses, checking under the couch, getting increasingly frustrated, and, well, you can probably guess where this is going.
No, I've absolutely been there.
Right. They were literally on my face the entire time. And it kind of hit me that this is exactly what humanity has been doing with the universe. I mean, the most spectacular, violent cosmic events are sending ripples straight through us right now. But we've been missing them simply because we didn't have the right glasses on.
That is a surprisingly perfect analogy. We have been completely blind or, well, numb to gravitational waves for most of history.
Yeah, and today's deep dive is all about the machine that is going to fix that, right? The Einstein Telescope, or ET.
Yeah, exactly. I mean, we've caught a few of these waves with our current surface detectors like LIGO, but ET is a proposed third-generation ground-based detector. It requires this completely radical new architectural approach to give us a tenfold increase in sensitivity.
Okay, let's unpack this for a second. Tenfold sensitivity is huge. But an interferometer basically just bounces lasers down really long tunnels to measure microscopic distance changes, right? So why not just build a bigger LIGO on the surface?
Because building bigger on the surface hits a very hard physical limit, which is Earth itself.
Wait, Earth is the limit?
Yeah, seismic noise. So trucks driving miles away, ocean waves crashing, even minor geological tremors, they all shake the mirrors. So ET has to go underground. We're talking 250 to 300 meters deep in stable rock.
Oh, wow, that is deep.
Yeah, they're looking at proposed sites in places like Sardinia, Saxony, or the Meuse-Rhine-Jura region. But, the real breakthrough isn't just the depth, it's the xylophone configuration.
The xylophone, meaning it's, what, tuned to different frequencies or something?
Exactly.
How do you physically build a xylophone into a giant laser detector?
By actually splitting the job into two different instruments operating simultaneously. One focuses on low-frequency waves, and to do that, it has to be cooled to cryogenic temperatures. We're talking around 10 to 20 Kelvin.
Okay, the cooling part makes sense. I mean, at room temperature, the thermal noise, like the actual atomic vibrations of the instrument itself, would totally mask those slow, subtle rumbles of massive black holes merging.
Right, exactly. But for the high frequencies, you don't need cryogenics. You need raw power to push through the quantum fuzziness of the light itself. So that second instrument runs at room temperature, and it blasts a massive 3-megawatt laser.
Wait, hold on. You're putting a 3-megawatt laser, which has to generate just an insane amount of heat.
Oh, massive amounts of heat.
Right next to an instrument cooled to near absolute zero. How does it not just, instantly cook itself?
Well, that is the immense engineering challenge they're working to solve right now, but it's absolutely necessary. It's like trying to record a delicate whisper and a booming bass drum at the exact same time.
So a single microphone just gets totally blown out by the drum.
Right, or it misses the whisper completely. So the xylophone design splits the job.
Okay, so it's kind of like wearing thermal night vision goggles and polarized sunglasses at the exact same time, just to make sure you never miss a single detail.
Yes. And if we connect this to the bigger picture, this hardware upgrade fundamentally changes our view of the universe. We go from detecting maybe a few events a week to up to 1 million events a year.
1 million events.
Yeah, and we'll be so sensitive we can peer all the way back to redshift 100.
Redshift 100. Wait, that's looking back to the cosmic dawn. We're talking about the very first stars ever formed.
Population 3 stars, yes. The very first generation of stars to ignite. ET is going to routinely observe the mergers of the black holes born from those exact stars.
That is just mind-blowing. We are literally going to listen to the echoes of the universe's first light.
It's incredible. But here is where the physics runs headfirst into a massive bottleneck.
Let me guess. The data.
Exactly. If ET catches 1 million events a year, that's an alert every few minutes. Human scientists literally cannot look at that much data.
Right, so we build a machine so incredibly sensitive that it generates a data avalanche way too massive for our own brains to process.
Yeah, we need automated help just to look at our own findings, which is why researchers are already testing agentic AI to step in. They actually just ran a test where they fed simulated ET gravitational wave data to AI agents.
Which ones?
Specifically Claude Code and Codex. They just gave them the parameters and let them work completely autonomously.
Okay, here's where it gets really interesting. And speaking of AI agents, this podcast is sponsored by Embersilk. Need help with AI training or automation or integration or software development, uncovering where agents could make the most impact for your business or personal life? Check out embersilk.com for AI needs.
That is perfect timing, actually.
Right. So wait,
Oh,
how autonomous are we talking with this ET data? Are they just flagging anomalies, or are they running the actual data analysis pipelines themselves?
they are running the entire pipeline. It's fascinating. Claude burned through the analysis in just 3.4 minutes. Yeah, though it did make some silent corrections along the way. Codex took a bit longer, about 16 minutes, but its process was highly auditable.
Like, it showed its work.
Exactly. It explicitly documented its self-correcting restarts, and it even went out of its way to run an unsolicited performance optimization on the math.
That is so cool. So basically, we are building this massive underground cryogenically cooled megawatt laser structure to catch ripples from the dawn of time, and we're relying on AI agents to do the math for us before we even wake up.
Which leaves you with this to ponder. If these autonomous agents are processing the data pipeline that quickly and intelligently, what happens when an AI spots a completely new physical phenomenon in the ET data before a human even glances at the screen?
Oh man, I mean, the universe has been putting on this spectacular show this whole time, and we're finally building the right lenses to see it. And, we're letting AI help us watch. Talk about a brilliant time to be alive.
It really is.
Well, if you enjoyed this podcast, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.